All right, everyone, let's settle down. Great weather to be here, walking all the way from Hampton. um, all right, so I think what I'm planning to do today is pretty much finish out the handout that I gave you last time, and then there's a separate handout, a one-page handout for today, and then this will will be a topic that Dr. Liu will do some examples on Friday. She does not have office hours today, but instead I'll hold office hours from 3 to 5 in my office. So if you have questions on the homework, feel free to drop by. Um, any particular questions from the homework or the lectures before we begin? Go ahead, Joe. The moment, you mean the torsion problem? Okay, sure. So I think, yeah, let's see. Let me pull up a separate page out here. So if I remember correctly, the problem on the quiz was that there is a fixed end, and from there it's a 4 feet out this way, 2 feet out in this direction, and maybe I'll mark the XYZs also. So this is X, this is Y, and this is Z. And there was a final leg of that problem out here. So we had a 2 kip load out here. The dimensions were, I believe, 2 feet, 4 feet, and 4 feet, right? Is that the problem? So the first thing I would want to see in this problem is what are the fixed end reactions? What do you think would be the reactions at this end? Maybe I'll label them too. This is A, B, C, and D. What would be the fixed end reaction forces and moments out here at A? So sum of forces in the y direction immediately tells me, of course, that there has to be a reaction 2 kip up there. How about the moment? Think about it maybe a little bit physically also. If you have a bar that is bent into that shape and you're holding it on one end and you're applying a load on the other, what kind of moment would you be applying on the fixed end? Torsion. Would there be any bending moment also? Yes? No, there won't be any bending moment, right? Because clearly I could have any structure between A and D. It could have been there or whatever structure it is there. It's fixed at point A and the load is applied at point D. So the only moment that the force creates, this force at D creates about point A is this 2 times this 2 feet, right? And that would create a pure torsion moment about A in the negative X direction. So the let me see if I was creating that way. So I'd have to rotate it along with the right hand roll in the other way to try to keep it in equilibrium. So the torsion moment that I would, or the reaction moment at A would be in this direction in the magnitude of 4 kip feet. Okay, so that's the first thing. I hope you are convinced that there won't be any bending moment at that point. Now, for the shear force diagram, hopefully you all saw that it was very similar to the example problems that we did. Shear is throughout 2, depending upon your convention, either positive 2 or negative 2 throughout the length of that bar. How about the bending moment? We know that in this portion of the beam, we would have a negative bending moment since it's going to bend downwards, down this way. It reaches 8 or minus 8 kip feet out here. Where does that bending moment go? It becomes torsion in this guy, right? So maybe I'll draw that as a separate torsion diagram. So, uh, so if this is my structure and my torsion diagram, so this is, let's say, M and this is T, then the torsion diagram clearly would not have any torsion in this last leg, and this 8 kip feet would become a torsion in which direction? Well, actually, it's internal, so depending upon the cut, it will be equal and opposite. But looking from the point of view of BC, it's going to create a torsion in this direction. So I'll say it's positive Z. But again, that also depends upon your convention. So I'll say it's positive 8 kip feet torsion. What about bending moment here? How do I try to figure out what's the bending moment here? Was that? There's constant shear, but what value should I start at? Yeah, we should indeed, of course, start at 0. But another way to look at it is this, that if you remember back from statics, the concept of equivalent forces and moments. So if I move this force from this point to this point, I also need to apply a moment in order to do that, and that moment was 8 kip feet. So the original problem is equivalent to this problem that I just drawn here, right? 2 feet moves that way, and in addition to that, if I apply torsion, then AB and BC would be acting exactly the same way as it was acting in the original problem. Does that make sense? So in now, using this, I can see that torsion is not going to cause any bending moment here. I know that this guy will cause bending moment, also negative. So it will just be a negative bending moment out here. And maybe what I do is I'll undo the change that I did here so that I can go back to that. And now I know that there's a negative bending moment of 4 kip feet here. That negative 4 kip feet goes where? It becomes torsion in the leg AB, right? So that, if you look at the leg BC and AB, the leg BC is coming under bending like that, and it's going to create a torsion on the leg AB. So that torsion will be in the amount of 4 kip feet in this direction. What about the bending moment in this guy, in AB, the last leg? So, couple of things to note here. There is torsion 8 kip feet out here, right? So if I take um, if I take out this leg, maybe keep this back here. So if I look at this structure, in this structure, this leg BC is under a torsion of 8 kip feet. That torsion will translate into bending in the leg AB. Hopefully you can see that. So this hand right here is AB, this this member out, small member out here is BC. If this guy is in torsion, it's going to want to turn the leg AB upwards. Would that be so? Would that be a positive bending moment or a negative bending moment? Positive bending moment, right? So since BC is turning counterclockwise, it is going to apply a positive moment on AB, and it's going to start at the same value as the torsion, which is 8, and go back down to 0 at the fixed end. Okay, it's going to go back down to 0 at the fixed end. So this is 8 kip feet, and this is positive, which is quite counterintuitive. Say that again. Any question? You had a question?
Oh, I thought shouldn't there be a moment at the fixed end?
Why would there? There is a moment, but there's only a torsional moment, right? So that was the first thing we determined. that the reaction moment at the fixed end is only a torsion moment. There's no bending moment at that point. Okay? So starting from 8, it will go down to 0. Which means, if you think about it, that the leg AB, which is fixed to the wall at A, that leg has a positive moment, right? That, so point B, would it move upward or downward? Upward. So even though the force to kick is downwards, point B moves upwards. That's sort of the strange thing about torsion. Okay. All right, so I'll let you digest that. Move this back here. And the video would be up online, so you can take a look at this in more detail if you want, Spencer. Friday. I'm almost done with that, but I need to go through more. Okay. Question, Mubin? Sure. How would the deflected shape look like? So we know that this guy goes slightly up this way. That guy starting from that deflected point will deflect downward this way. And then this guy would deflect further downward this way. So yeah, torsion can do funny things, but I think again, I'm mainly looking for whether you set up the problem correctly or not, and whether you are able to figure out how the torsion in one member goes to a bending in the other, how the bending in one member goes to the torsion in the other. And I think there's quite a few of you who did not get this problem correctly, which is understandable. But of course, this means you need more practice on torsion problems. But don't worry about that. I think you're all in the same boat. Okay. All right. So we'll go back and try to finish out. We'll go back and try to finish out this topic on the force method for truss problems and force method for composite structures that I on the handout that I gave last time. We've already done force method for beam and frame problems, and essentially the idea was to first of all decompose into a underlying determinate system, find the displacements or rotations under the actual loads, find flexibility coefficients, and then use compatibility to solve the unknown reactions. And that's exactly the same procedure that we are going to do for trusses. But for trusses, we have to be slightly more careful on how we determine the underlying determinate structure. So for example, I was telling you last time, if I have this indeterminate truss, the degree of indeterminacy is indeed 1. If I remove that, now this becomes a determinate truss. So let me put that back in. With one member, one additional unknown, it is an indeterminate truss. So the way that the way that I told you to come up with a underlying determinate structure was to make a cut to release the internal force in one of those members. I'm going to make a cut here, which means that at the location of the cut, when I apply the actual load, that location of the cut might separate or it might overlap, right? It will have incompatibility at that point. So what I'm going to do then to make it compatible is to apply equal and opposite unknown FAC forces, though that would be the internal force or the redundant internal force that I'm trying to find. Under the action of a unit load here, I can find what the displacement would be for that at that cut. And that would be the flexibility, which I'm calling FAC-AC in this case. AC because it's actually a member. It's not a particular point. FAC meaning displacement, relative displacement within AC caused by a unit load applied on AC. So that was the concept that we said. And if I take that flexibility multiplied by the unknown force and add it to this, then I get the compatibility equation, which I'll write it like this. Compatibility would be simply that delta AC plus FAC AC times the unknown internal force AC equal to 0. Under the action of the actual loads and the redundant loads, the displacement at the cut has to be 0. So the actual load causes the cut to separate, and the redundant force is applied in such a way that the cut comes back and matches exactly. Okay. So that's sort of the logic here. Let's take a look at the example, which I had barely started last time. This is a truss. This is indeed a truss. I think we were discussing last time what is the degree of indeterminacy of this truss. And I told you again that if you remove the member BC, it becomes this member BD and AB with a load of 800 pounds applied, which is very similar to your homework problem 1, if you remember that, and that was determinate. So removing one member makes it determinate, meaning, of course, degree of indeterminacy is 1. We don't only look at the number of reactions in this case. The number of reactions, even though they are 6, and for the total structure, the structure is not a structure that can maintain its shape, right? It is a mechanism. If I remove the supports, then it becomes a mechanism. All the 3 legs can move whichever way they want. So that's why we need to consider all of the legs separately. And if you do that, I told you last time, 10 unknowns and 9 equilibrium equations, and therefore still the degree of indeterminacy is 1. And the idea here is that we'll cut here, apply the actual load. Let me ask you this: is this structure determinate? This structure on the left, is this structure determinate? Yep, because if I make a cut here, this cannot carry any force, which is just a 2-member truss pinned on both ends, and with a load, I can use equilibrium to find the internal forces in this. And without going into the calculations, assuming that you know how to do that, maybe I'll just draw the free body diagram here. This is B, this is 800, and there is unknown force BD out here and unknown force AB out here. 2 unknowns, 2 equilibrium equations. I'm sure you can solve it, and if you solve it, you should get 666.67 pounds on that, and negative 666.67 pounds. It's a symmetric 3, 4, 5 triangle, both above and down. So this is the force that you should get. That's the response of the actual structure. And note that both of those legs would be 0 force members because there is a cut there. Now, the redundant part of the problem is that I apply a unit load here and try to close the gap that must have opened up during this stage, right? So in stage 1, I cut the member, I apply the load. Now this member might separate at that point, or it might close back up, overlap at that point. I need to apply these unit loads out here and multiply them with some unknown force BC so that I get compatibility at that point. So that's the logic here. And once again, with this unit load, if you calculate the internal forces, we will get minus 5/8 compression in this leg, minus 5/8 compression in this leg, and these 2 separate pieces would also be in tension in the amount of 1. So that's an important thing for trusses that we need to keep in mind. This would be 1, this would be 1. Okay, so we've done the underlying determinate structure and the determinate structure subject to a redundant force. All we need to do now is to figure out what displacement this point had and what displacement this point has, which is the flexibility and in-force compatibility. So in this case, compatibility, I'm going to write that here. This is delta BC under actual loads, and this is FBC BC is the flexibility that I'm trying to find. Okay. So what would be the compatibility equation, Scott? What would be the compatibility equation for this piece? Go ahead. Hongzi, go ahead.
Delta BC
Okay. Delta BC, which is the actual displacement under the applied load.
plus BCX at BC.
So actually, I should write that in black because it's known. So delta BC plus FBC BC, that's the flexibility under the unit load, times the unknown force BC. And so essentially we are saying that the displacement due to the actual loads and displacement due to the redundant loads must add up to 0, and that's the compatibility equation. So I can solve this equation if I know what delta BC is and what FBC BC is. So the only unknown here is this internal force, redundant internal force BC. So the problem now becomes, how do I find delta BC and FBC BC for this particular problem? How do I find that? Would you be able to calculate this delta BC? Maybe take 30 seconds and see if you can set it up. How would you go about calculating it? Say that again, Ivan. Horizontal displacement at B, actually, yes, there in general there can be some horizontal displacement at B, but that horizontal displacement is not really what we're looking for. We're looking for the separation at the point of the cut. That's so horizontal displacement might be related to that, but you'd still be missing some piece there. Go ahead, Aaron.
Subtract BL over AD from that.
For this particular problem, yes, that will work because this is laid out horizontally. And if you find the horizontal displacement at this point, yes, you can. And actually, this will be a zero force member, so it won't have any displacement. It would be equal to that cut. But in general, if I have an inclined member, your logic will not always work. So in general cases, what you should do is to realize that this is nothing but the virtual work method. If I want to find out the displacement at some point, and in this case, I want to find the relative displacement at the same point, then I would apply a unit load, equal and opposite unit loads at that point, and I would use the virtual work method to find out the relative displacement at this point, just by using virtual work method for trusses. So let's see how that is done. Since I want displacements at that point, I'll apply P prime and minus P prime at that point, which again at the end will cancel off. So I'm just applying 1. And we will, according to the virtual work method, I will have virtual internal forces, small nm, and I'm going to write that as a prime as well because it's virtual forces, times real displacement of each one of those members. Real displacement of each one of those members is nm over AE. And I need to sum that up over all the members. You remember this? Hope this looks familiar. So in this particular problem, the virtual force, there's virtual force is -5/8, and the real displacement is 666.67 times 5 feet divided by AE in one case, and plus -5/8 times 666.67, or negative actually. So negative times 5 over AE. And clearly both of those terms cancel off, and what we get is 0. So for this particular problem, it so happens that the displacement at the cut under the actual force is 0. Okay, which means what? What would be the value of BC if delta BC is 0? 0, right? And we'll do that, but let me first ask you, what is FBC BC? How would you calculate that? That's the displacement at this point when I apply a unit load, also equal and opposite unit loads at that point. Would that be 0? Would FBC BC be 0? No, right? Because if I'm applying a load to a structure, it has got to deform. So, and that deformation under a unit load is basically what is the definition of flexibility. So we need to find this flexibility in general just to be able to calculate BC, because in general that displacement may not be 0. So let's see how we would do that. How can I find the displacement at this point under the load at the same point? Again, the virtual work method, right? Which would be basically that take the virtual internal forces, that would be Nm prime, times the real displacement. But for this particular problem, the real and the virtual system is the same. And this also happened with our beam or problem and also happened with our frame problem, right? The redundant system that we have ends up being the real system and the virtual system when we want to calculate flexibilities. So this is going to be a common theme throughout. And then we have Nm Lm over Ae, and we need to sum that up over all the elements m, which just simply ends up being Nm square L over Ae. And if you do that, you should get minus 5 over 8 times minus 5 over 8 times times 5 over AE, and I'll take that entire thing, multiply it by 2, because there's this leg and this leg that I'm usually you would do this with a table, right? But there's only 3 members here. I don't really need to make a big table here. Is there anything else that I need to account for? Right? Anything else we need to account for? So we are summing up over all the members. We have counted this member and this member. What about this member? Do we need to account for that? Yes, because I am applying 1 and 1 equal and opposite here. So these two separate pieces of the member also store internal energy, right? So we need to account for all the internal energies in our system. So we would have, what would be the virtual force in those two members? Just one. The one force, one virtual force that I had applied, and the displacement would be 1 times, I believe that's 4 feet. Yep. 1 times 4 divided by AE. And if you calculate that out, it should come out to 29.6 over AE. And I'll write this 0 properly. So that ends up being 0. And immediately you can see that BC is equal to delta BC divided by FBC BC, which simply is 0. So the response of the indeterminate system the response of the indeterminate system turns out to be that the member BC is a zero force member, and this guy is in tension 666.67. This is in compression, same amount, and that's basically the solution of the indeterminate structure. For this particular problem, it so happened that this horizontal member came out to be zero force member, but of course in general it will not happen always, right? Now at that point, most of the problems that you might encounter will stop, like find all the internal forces, and that's it. But we can go a step further. The problem really here asks you that what is the vertical deflection at P? So we have just determined all the internal forces in all those members. The second part of the problem says what is the vertical deflection at B? How do you do that? Virtual work method on the indeterminate structure now, right? So virtual work method on the indeterminate structure, indeed I would apply a P prime here. I already know that under this P prime, I would get 5/6 P prime tension here, minus 5/6 P prime compression here. All I'm doing to do that is to scale this value by P prime divided by 800, right? I have the solution to the indeterminate structure. If I just scale this value by P prime over 800, I'll get these things. And as before, this middle member turns out to be 0. Drew? This is indeed 5/6 because, well, I guess 666 divided by 800, and if you multiply that by 3, I suppose you should get, well, let's do that. Anybody has a calculator? Can you do that? 666. Right. So, and then you also need to take 3/5 of that. So, okay, let me do that here. So if I have P prime this way, and I have an unknown BD and AB here, in general, I would also have this BC, but I already know that this would be 0, so I'm not drawing that, which makes it a determinate problem now. The equation would say basically that 2BD cosine of that angle, which is, sine of that angle, which is 3/5, has to be equal to P prime. So clearly 2 times 3 is 6, 5 goes the other way, so we get 5/6 P prime. Okay. Yeah, 5/8 was actually when we cut this member, so that's a different loading scenario. So yeah, back to this problem now. If I want to find the vertical displacement at B of the indeterminate structure, I would need to apply P prime here, find the internal forces, which is just obtained by scaling these guys, and then use the virtual work method. So I would get on the right hand side 5/6 P prime times 666.67 times 5/AE, and plus we get a minus 5/6 P prime times a negative 666.67 over AE. So clearly these two add up, not cancel off. And on the left hand side we have a P prime times the actual displacement delta B. We cancel off all the P primes. And if you follow through with the calculation, you should see that what we have is is the displacement at that point, just using the virtual work method. So in general, for problems with the force method, where even if the structure is indeterminate, the most important thing to find first of all is the redundant forces. Once you've done that, calculating the displacement at the point of application of the load is not too much extra work. As you can see, we've already solved everything. All we need to do is to apply the virtual work method, sum up the internal energies, and we get the displacement at that point. Displacement of the indeterminate structure. Okay. Questions about this, Miles?
Why did you not multiply by 5 on your second one?
Sorry, I should have. Yes, thank you. That's NL over AE. Anything else? Okay, so I'll let Dr. Liu do maybe a couple more problems on this. And let's go to composite structures. Looks like we're running short of time again. So composite structures really are what the name says. It's a composition of beams, frames, truss, in general, any other type of structural element also. Sometimes there might be cables, strings, solid elements. Anything could be there. But what we are going to restrict our attention to is structures which are composed out of beam or frame type elements, which is clearly this member A, D, C here, and truss members. So these three members up here, they are truss members, which you can see hopefully are connected with gusset plates to the beam. And application of these types of structures, can you think why somebody might want to do this to this beam, which carries a load of something here? Why would you want to do something like that, Miles?
Reduce the
Right, so if this truss was not here, then this beam would be forced to carry that entire load by itself, which would need a very fairly bulky beam out there. So, for example, if a company had the crane and later on they wanted to lift bigger loads, they would just supplement or augment their structure with, strengthen their structure with additional truss members just to be able to redistribute the loads. So they come in, these composite structures come in handy that way. In this particular problem, the problem says determine the forces in these three members, determine the deflection at the point C, and draw the approximate deflected shape. Assume that point A, assume that this point A, when it's fixed to the wall, is a pin, not really a fixed end. And E is a roller. Connections between the truss members are, of course, pins, and the properties are given. So first question, is this a determinate structure or an indeterminate structure? And maybe let me step back a little bit. Maybe if I did not have the truss members, if I just had the beam with a pin joint here at A and a roller at E, would that be a determinate structure? Yes, it's a simply supported beam with an overhang, right? Now if I add these two or these three members, maybe let me add two members at a time. So add AB and add BC. I'm not adding BD yet. Okay. If I add only those two members and apply a load, what would be the forces in those two members? Even after deflection. So I don't have my beam when I need it. If I have this beam with a truss member, only two truss members connected out here, right? And if I apply a load at the free end, it deflects. What do the truss members do? They just deflect along with it, right? They don't really carry any load because they just reconfigure, they change the angle between themselves, and they don't really carry any load. So even that structure is determinate because those two members would be just zero forces. It's only when I add this member, it becomes indeterminate. Now you cannot solve for all of those because these members will indeed carry some forces. And since I'm adding one internal force, one redundant internal force, therefore the degree of indeterminacy of this structure is 1. Okay, so one way to determine whether something is determinate or indeterminate is to write all the equations, write all the unknowns, and see whether you have enough to match up. The other way is what I just did. Take an indeterminate structure and start knocking off elements, and the number of elements you knock off is the degree of indeterminacy. Okay. All right. So in this particular case, as I said, this would be my underlying determinate structure where I've cut the member BD and I apply the actual load 30 kips. I can find the reactions easily just by equilibrium, 40 kips, 70 kips. And I can draw the bending moment diagram of this entire structure. Note that, as I said, these two members would just be zero force members. Because of the cut, these two members would also be zero force members. The truss does not take any load if I cut this member. So what would be the bending moment diagram for ADC? What would that look like? Positive or negative? Negative throughout, right? Because the deflected shape will kind of look like this. It's a simply supported beam with an overhang. So it's all frowny face all throughout. So indeed, we will have a negative bending moment throughout. It would be zero at the two ends, and we would have a big negative moment at D or E. And we can find that just by taking a straight line out here and a straight line from that point. That's my bending moment diagram. The value of that point would be 30 times 4. That would be 120. So minus 120 kip feet. And if I start measuring, let me say x1 from this point, then this equation would be minus 30 x1. And if I measure x from the other end, then this guy would be minus 40x on that half, right? So with that, I can find out I can try to find out the displacement delta BD1, because under the action of the load, these two ends in general will separate, right? And to find out that out, I'm going to use the virtual work method, apply equal and opposite unit loads out there, and figure out all the internal forces. This is also a determinate structure because I have that cut here. And then I can use compatibility to solve for that internal force. Okay, so let's do that. In this particular case, if I apply a unit load out here, hopefully you can see that the free body diagram of point B looks like one down here. And just to be consistent with everything, I'm going to draw AB and BC, assuming them to be in tension. They will come out negative and they'll be in compression. So with this free body diagram, you can set up the two equilibrium equations. I'm not going to go through the details. I'm sure you know what that is. And you find the values that BC is minus 0.7143 and AB is minus 0.8081. The two halves of BD are just in 1 and 1 tension, right? So I know the forces in all of these truss members. And now if I look at the beam out here, ADC, that beam is in these types of forces. One, pulling up because this member is in tension in the amount of 1. There is this force pointing down in compression, and there is this force pointing to the right in compression. Let me ask you this. When I apply this 1 and 1 force here, what are the reactions at A and E? Under this loading scenario on the right hand side for the redundant structure, what are the reactions at A and E? It's a determinate structure, so you can find that. Go ahead. What would be the reactions at A and E if I apply 1 and 1 at this kept? 0, right? Because we are applying equal and opposite forces at the same point essentially, and the structure itself is equilibrated, so there's no need for external reactions anywhere. So these AD would be 0, and that's why I'm not drawing any reactions at the bottom of the beam. And given a beam under these types of loadings, once again with the same logic, you can draw the bending moment diagram for that beam. Now I have the response of the actual underlying structure and the redundant structure. Now the big question: how do I find delta BD1? How do I find the displacement at the cut under the action of the real load using, no surprise, the virtual work method? What all do I need to do to calculate delta BD at this point? So since I need the relative displacement at delta at BD, I'm going to apply a P prime at delta BD, and P prime cancels off, so that I'll use this structure as my virtual structure. This structure will be my real structure, and I can calculate displacement at that point. So very quickly, but in this case, we need to keep in mind that I need to add up both energies due to bending and due to axial effects in the truss members. Thankfully, the axial effects in this particular problem are all 0. In general, that would not be the case. So in this case, I would have sum of the virtual internal forces times the real displacements, and plus the virtual bending moment times the real curvature, and integrated over the length of the beam. In this particular problem, the first energy stored in the truss part is 0. So all I need to do is to sum up the energy stored in the beam. And looks like I've run out of time here, so we'll do all of that next time, and then we'll try to enforce compatibility and flexibility and all that. Okay. So I'll see you all. Well, actually, I'll let Dr. Liu complete this. So we'll see you on Friday.